Hi everyone, so we're just going to talk about applications of exponential functions. What we've done so far is we've done a lot of work around exponential functions, graphing them, solving equations, but we're now going to apply them to real life situations. So we've got a situation here where we've got population of bacteria. You'll often see exponentials being applied in situations with growth and decay. So we've got this population of bacteria which is increasing at 30% per hour. We've got to think about, if you're going to increase a quantity, any quantity by 30%, what would you multiply that by? Well, if you multiplied it by 1, you would increase it by just itself. If you multiply anything by 1, you get the same thing. So you're not actually increasing it at all. So if you want to increase something by 30%, you're going to have to get some extra. And so you'd multiply it by 1.3. Now, you think about why that is. Well, if you're increasing something by 30%, you want to find 30% of that thing, so you do 0.3 times it, and then add that to the original. So that's the same as multiplying something by 1.3. So you multiply it by 1.3. So if we've got an original population of bacteria, and our original population is, as we can see here, 20, and T is the population after T hours, PT is the population of T hours, then we know that P0 is actually going to be, if P0 is modelled by this, we know that P0 is just equal to 20. If we were going to do P1, we'd have to do 20 times by 1.3. Now if we were going to do P2, we'd go 20 times 1.3, and then we want to increase that again by 30%, so we'd times it by 1.3 again. In other words, we could go 20 times 1.3 squared. P3 would be equal to 20 times 1.3 raised to the power of 3. So in general then, we could go and say that Pn would be equal to 20 times 1.3 to the power of n. And there you have an exponential function. So we can often describe exponential growth and decay by something of this form, where you've got something multiplied by another base number raised to a power. So it could be something of the form a equals a0 times b to the t. Now, whether you use a or c or d or f doesn't matter, or b doesn't really matter. But a0 is talking about the initial amount, so it's often times by initial amount, and then you've got the growth factor happening over here. So A0 is the initial, and B is a positive constant. So if B is greater than 1, as we can see in the model above, the model will actually represent growth, whereas if B is less than 1, the model will represent decay. Okay, and we'll see some of that in some examples. So we've got an entomologist who's monitoring a plague of locusts, and we've got the function there where n is the number of weeks, and we're asked to find the original affected area. So if we want to look at this question, we've got a of n, which is the amount, the area, and then we've got n, of course, which is the time. So the original affected area is when n is going to equal 0. So a of 0 is going to therefore equal 1000 times 1.15 to the power of 0, which is always going to be 1, so you're going to get 1000. Okay, and if we're doing the area, we want to say what the area units are, so it's hectares. So you can read straight off from the equation what the initial is. Then what is the percentage increase? Well, we're going to get that from looking closely at our equation and remembering that the growth or the decay comes from this little bit in here, and that's 1.15. So that means we've multiplied by itself, that's by the 1, then we've also multiplied it by an extra factor, the 0.15. So we've actually increased it as a 15% increase in the area affected. Then we're asked to find the affected area after 5 weeks and then after 10 weeks. So after 5 weeks, we're going to substitute that in. Pause the video and have a go at doing it yourself. So hopefully you managed to substitute in 5 for time, and you got 2010 hectares, and then you substituted in 10 when we were trying to work out the 10 weeks. So that's a pretty standard example. Now the next we want to draw the graph. And when you're drawing the graph of this stuff, you want to make sure you're using the information that you've actually got from the previous question. So if you've worked out some things in the previous question, you need to make sure that that ends up somewhere on your graph. Now if we look at that, hopefully you can see straight away what the asymptote is going to be. And you should be able to see that, hey, there isn't actually going to be an asymptote other than the asymptote at 0. There is an asymptote, but it's an asymptote at y equals 0 along the x-axis. Okay, so I'd make sure, because this is an application question, that I'm labeling my axes with the information that I've been given. So this is a of n up here, and I would put the units. I would put hectares, and then this is n down here, which is in weeks. So make sure you put those, and you don't want to lose marks for just missing silly things like that. Then we need to plot all the other bits of information. So we've been told that A0, at 0 we go to 1,000. We're going to get all the way up to 4,050. But if we read through and sneak through the question, we also want to be able to get to 8,000 at some point. So if I look at 1, 2, 3, 4, 5, 6, 7, 8, yep, I can fit that in. So this is going to, and you can do it really accurately on yours, hopefully, my stylus. That's going to be 2,000, that's going to be 4,000, that's going to be 6,000. That up there is going to be 8,000. Okay, so that's going to be 0, and that is going to be 4,000 there. Labeling my axes. And then along here, well, we've got to get to 10 weeks at least, because we've got that in the question, but also at 10 weeks we only got to 4,000 hectares, and we want to get to 8,000 hectares. So we're probably going to need more than 10 weeks. Say we need 15. So go 1, 2, 3, 4, 5 there. 10, 15. Okay, so we go 5, 10, 15 weeks. And so then if we plot all the information we've got, we're going to have, well, at 0 we're going to have 1,000. Okay, so the amount of hectares is going to be 1,000 right there. And at 5 weeks it's going to be 2,010, so it's just going to be a bit above there. Ooh. And that's probably a little bit too big, but you can work it out a bit more accurately in yours. Then at 10 weeks we're going to go 4,050. So again, it should be just above 4,000, pretty much on 4,000. And then we want to plot we want to be able to see what's happening at 8,000. We don't know exactly. So we're going to use that as our trend. We're going to go along the x-axis, make sure it's clear that we're not crossing that x-axis because we're asymptotic to it. We're going to go up there. If you can do the points in a different color to what you've actually plotted, that will help distinguish it. Okay, and there we go. Then determine how it would take for the affected area to reach 8,000 hectares from our graph. So we're going to go up to our graph and go, well, there's 8,000 there. I'm going to read across from there and read down from there. As you can see, I'm not doing that very accurately, but it's about 14 weeks, approximately 14 weeks. So approximately 14 weeks. And if you did it on your calculator and you graphed it on your calculator, and then you fixed up the window, and then you did gsolve, and then you found the x value, so you do xcalc because you've got the y value, then you would have got 14.9 weeks. Okay. All right, another example. This one's a little bit different. The number of bacteria in a culture increases exponentially with time according to this rule, n equals a times b to the t, where t is measured in hours. When observation started, there were 1,000 bacteria, and 5 hours later, there were 10,000. Find A and B. All right, so all you've got to do here is think about what information have I been given. So when observation started, there were 1,000 bacteria. 5 hours later, there were 10,000. You've been given 2 pieces of information. You know that when t equals 0, n is equal to 1,000. That's one bit of information. And you know if you're going to try and find 2 unknowns, you need 2 bits of information. Now we know that n equals ab to the power of t. And so 1,000 equals ab to the power of t. And so therefore, if we try and work that out, that's as far as we can go, except we know that at this stage, t is equal to 0. So that's going to be ab to the 0, so you know what a is. You know that a is 1,000. And that's going to help you be able to find b. So if we substitute that in, when t equals 5, n is going to equal 10,000. And so we get 10,000 is going to equal 1,000 times b to the 5, because I've substituted in a there, so this is just a. If we take it one step back, remember we're substituting into this up here. Okay, and so n is 10,000 and a is 1,000 from before. And so if I divide both sides by 1,000, I get that b to the power of 5 is equal to 10. And so I can just say therefore that b is equal 10 to the 1/5. You're taking the 5th root of 10 in order to find b. So therefore n is equal to 1,000 times b to the 5th. Alrighty, one more example. Here we're talking about the equation of a decay function in this case. So decay is going to be a little bit different, and if we think about it, before we said that in order to get a growth function, we often had something where we had a equals a0 times b to the t, and if p was greater than 1, it was growth. If p is less than 1, it is decay. So just remember that. This is talking about half-life, and half-life is just the measure of time until half of the mass remains. So the measure of time until half of the mass remains. So we don't actually have to have the equation to be able to draw the graph of this. If we think about this, if we've got our axis here, and we've got a certain weight, and of course weight can never be less than 0, and we've got time over here in days, how can we draw this? Well, we know what the initial weight is. We know that the initial weight is, if we're going in the same units, is grams. So we've got here that the initial weight is 20 grams. Okay, now we've got a half-life of 2 days. So that means after 2 days, half of that is going to remain. So after 2 days, we're going to get all the way down to 10. So if I go to here, and then I put my scale out here in terms of 2. So after, so that's the initial at 20 there. This is going to be 10 there. After 2 days, we're at 10. And then after another 2 days, we're going to halve again, so we're going to be at 5. And another 2 days, we're going to halve again, so we're going to be at 2.5. Right there. And then another 2 days, etc., etc., etc. And as you can see, we're going to get asymptotic to this x-axis, which is what we want. So you're going to go all the way down like that and get asymptotic to the x-axis. Really jagged, but there you go. There's your function. You've got your weight, you've got your units, you've got your different things that are happening. And if we think about this in terms of what we've got going on here, we've got W0, the initial weight here. Then we've got a half of W0, or 0.5 of W0, and then we've got 0.25 of W0, etc., etc., etc. So then we're asked to determine the equation of the decay function. Now this is a bit different because we could just do it and try and do it using to get it into this form. But it's actually asked us a specific form it wants us it in, so we have to be able to get into that form. Now this is not as hard as it might look, because all you've got here is one unknown, don't you? K. T is fine. You're allowed to have T, so all you have to do is find K. So we know that W0 is equal to 20. We've been told that. We've also got a lot of other information, but if we go straight from that, we can go that WT is therefore going to equal 20 times 2 to the power of KT. Now you might go, well, hey, sub in to there that T is equal to 0, and then you'll get rid of K. So That's the problem. So you don't want to do that. You don't. Yes, that's right. That when t is 0, that the weight is 20. But if you substitute in t is 0, you get rid of that whole 2kt thing. So you don't want to do that. You want to use another piece of information. What can you use? Well, you know that after 2 days, when t is 2, because of half-life, mass has gone down a whole half. So W is equal to 10 kilograms. So all you have to do, therefore, is substitute in W as being 10 and T as being 2. And so 10 is going to equal 20 times 2k to the power of 2. And so 2 to the 2k, if I divide both sides by 20, is going to equal a half. So 2 to the 2k equals 2 to the negative 1. Therefore, 2k equals negative 1, and k equals negative 1 over 2. And so, therefore, our final equation is going to be that Wt equals W0 times 2 to the power of negative a half t. Alright? And that's it. So they're not hard. You just got to use the piece of information that you've been given. Hopefully that helps with some applications of exponential functions.